Okay, second topic for this set of videos, pollution. Why two topics, you may ask? Well, it turns out that these two topics are super closely connected. Okay, and actually, I'm not going to spoil everything by telling you straight away why that's the case, but they are. And actually, yeah, this lecture is kind of based on an article that I just published in the European Economic Review, and also there's another article which is to do with the the hill and the ball and stuff that I also published last year in the Journal of the Association of Environmental and Resource Economists, which are both super good journals, and there's both of those articles are basically thanks to this course. That teaching this course has forced me to think a hell of a lot about this stuff, and led indirectly to those articles, so that's kind of cool. Okay, so what's this one all about? So remember, if we go back to the very start of the course, I'm not going to draw it again, we've got the one with the prices and the quantities. Yeah, that was for resources and energy, metals, fossil fuels. But when we look at pollution, what do we see? We see something similar. Let's call it P. This is pollution, not price. We see something similar, but then often it nosedives. Okay. Which isn't to say we've solved all the pollution problems, because this pollutant might have nosedived, but there's any number of others that are still going up. Yeah. So is this the exception, or is it a question of like, when do these ones nosedive? And even if these nosedive, are there others that are going to keep growing? Yeah. We're going to think about some of those questions today, or in this video, the next couple of videos. Okay, and we start just by explaining why we see this. And it's pretty straightforward, actually. The incredible thing is that it hasn't been done properly in the literature until now. So the seminal work, seminal means seeding, the work that seeded or sort of started this whole literature was Grossman and Kruger. They published it in stages, but 1995 is perhaps the most cited one. There's strong support for the idea that when the flow of a single pollutant in a single country is plotted against time, that flow will, in most cases, first tend to rise, and later, if enough time has passed, decline. Okay, so of course there's plenty of pollutants where it hasn't started declining yet, but so that it's, yeah, of course it's an open question whether they'll all decline, but we often see the rise and decline. But if we compare paths for the same pollutant across countries, it's hard to see patterns, right? It's not that they all pollution generally goes down at some level of GDP. It's not that for given pollutants, they don't all go down in the same countries at the same time, and they don't all go down at the same level of GDP either. And there's no theoretical, widely accepted explanation for this. We'll see if people buy my article. One reason for this is that researchers building theoretical models have fallen into the trap of treating pollution as an input to production rather than as a byproduct. If we think of pollution as an input in a Cobb-Douglas production function, then we know that the factor share of pollution must be constant. And if we let the marginal damage caused by pollution track income, a natural assumption, then the flow of pollution should be constant as the economy grows. So as we get richer, if we imagine that pollution damages are knocking out a proportion of our production, that's one way of thinking about it, then our willingness to pay to get rid of pollution will go up over time. But if we think of the pollution as an input in a Cobb-Douglas production function, so if we have ALL to the 1 minus alpha, P to the alpha, where P is pollution, so we need to pollute to be able to produce. If AL goes up, then WP, firms' willingness to pay to be able to pollute, it will rise. Okay. If P is held constant, WP will rise, because WPP has to rise, doesn't it? WPP is going to be alpha Y. So if Y is rising, WPP must be rising. But the willingness to pay to stop pollution rises. So if we assume that's reflected in policy, then WP will rise at the same rate as Y, which means P must be constant. So according to that way of thinking, P should be constant. So you shouldn't see the rise and you shouldn't see the fall. It's like it's kind of like a DHSS sort of model. And then, so if you have that kind of starting point, it's just super hard. If you start there, it's like, just don't start here. It's like the Irish taxi driver, or if you're Swedish, you could say the Norwegian taxi driver. You know, how do I get to Stureplan? Don't start here. You know, how do you explain the EKC or these observations? Don't start here. Totally wrong. Okay, so where do you start? You should start with thinking about where pollutants actually come from. Pollutants aren't inputs, are they? Where do pollutants actually come from? Typically, they come from the use of natural resources. You burn coal, what happens? Coal is the input to production. Pollution is the byproduct of the burning of the coal, right? So we've got Y is ALL to the 1 minus alpha, R to the alpha, and P, if P is the flow of pollution, is like beta R. Okay. Okay, so if this is it, end of story, then this is looking kind of similar, isn't it? Because we can take R and put P over beta in instead. But already there's an important difference, because in the profit maximization problem, then pollution is costing, because what does R cost? R costs WR to extract, doesn't it? So you've got two reasons not to pollute. One is that it's costly to pollute, even if there's no regulations, because to pollute, you have to burn coal. Yeah. So even if there's no regulation of pollution, you're not going to pollute hur mycket som helst. You're not going to pollute like loads and loads. How do you say that in English? Whatever. There's going to be a limit. The limit on your pollution will be how much coal you're going to choose to burn. Okay. But in addition, you might have to pay a tax. So it could be, I'm struggling now with the board. Never gone over here, but you might have to pay actually plus an emissions tax. Yeah. This should stay the same over time, right? From our data, the price of coal, for instance, stays the same, more or less, but this should grow systematically, shouldn't it? How is this going to play out? We'll find out. Let's see what it says in the notes. When we treat pollution as a byproduct of natural resource use, the analysis changes completely. The social costs of natural resource use are then the sum of extraction costs and the damage costs. Extraction costs, damage costs. At low income, the pollution damages are small. So if we're poor, we're not willing to pay much to avoid pollution. So this is small. Much smaller if we're poor enough than this. So this dominates, we can ignore this. At low income, pollution damages are small and the constant extraction cost dominates. And because the natural resource is an input in a Cobham production function behind me, natural resource consumption increases with growth, as do polluting emissions. So it's our favorite picture, Y, R, W, R. Yeah. And R and P are linked, so that's what we see. As income increases, so does the willingness to pay to avoid pollution. Tor here. Tau, if you like. I call it Tor. The social cost of natural resource use starts to rise and resource use levels off. So imagine this is growing at the growth rate. So early on, it's negligible compared to this, but after a while, it's going to dominate compared to this. This becomes negligible. And we have plus tau times R and Tor times R. And since Tor is growing at the growth rate, this Tor has taken over the role of WR. So now it's growing at the growth rate, and which is going to mean that R will level off. So far, we're predicting that if this is Y, pollution should do this. Yeah. And the price of, well, the price of pollution is coming from coal. The price of burning coal does this, where this is extraction cost and this is extraction cost plus the social cost of burning, of emitting the pollutant. We're assuming that this is with regulation. Yeah, it all depends on regulation. This comes from regulation. Okay. So we're getting somewhere towards this, but we're not getting this, are we? How are we going to get this? Have a think. This is the link to the previous video, right? Or the previous two videos. If there is a cleaner but more expensive alternative resource, there will come a point at which this resource is preferred and pollution falls dramatically. So if R is actually R1 to the epsilon, you know, we can say gamma R1, gamma 1 R1 plus gamma 2 R2 to the epsilon, or to the 1 over epsilon, where epsilon is bigger than 0. If this is the coal and this is gas, and we're worried about sulfur emissions, this is cheaper. So when we're poor, we use the coal. As we start getting richer, we start getting worried about the coal, and we start using less or putting a scrubber on or something. But after a while, we just say, look, WR plus Tor for the coal is less, WR1 plus Tor1 is less than WR2. Let's just switch to the gas. Okay. So at some point, as we keep getting richer, it gets worthwhile to switch to the more expensive but cleaner input if you have two inputs that are good substitutes. bigger than 0 elasticity. And if there's, what I prove in the paper is that if there's a perfectly clean resource, however expensive it is, we will at some point get to the point where we switch to that resource, if there is something perfectly clean. Okay. I think I'll stop this video here and then we'll do some math. Okay, so we'll divide things up.